Good morning to GWA Physics, and this morning I wanted to go back over some problems that dealt with objects sliding across flat surfaces, both with and without friction, and with forces that are not necessarily applied parallel to the surface. So let's start out with an easy one, and then let's work our way up and see if this makes some sense for you. These were problems off the first test that we had this 9 weeks. So if this is the surface, let's say it's the top of a table, and there was a box sitting on the table, and we usually drew it like this and said that the mass was going to be 5 kilograms. So we're giving you the mass of the box, but we're not telling you the weight of the box. So they say that this object, and the question would say, pushed with a force of 20 newtons. Okay, so you've got a box sitting on a table. It has a mass of 5 kilograms and it's being pushed with a force of 20 newtons. Let's draw this up and let's make sure that we understand where all the forces are. So first of all, you'll remember that we draw a dot to show the center of mass, and then we show all the vectors that have the forces that are acting on the box. So right away, we have an F of G, which is called the force of gravity. And the force of gravity is the weight, okay? And I'm going to write that right here. I would like for you to say, oh yeah, I remember that, okay? And F of G, which is going to be 50 newtons. Now, if you don't remember why that's 50 newtons, that's because M times G is the force of gravity. Secondly, we said on a flat surface, the normal force is equal to but opposite the weight. So if the weight is pulling down towards the center of the earth, then the normal force is pushing up, and it's equal to but opposite. So we're going to give that a value of 50 newtons also. Now, that normal force is what we refer to in class as a supporting force. So where's that normal force coming from? It's coming from the table supporting the weight of the box, okay? And then I'm going to arbitrarily decide that this thing's going to the right. So I'm going to put a vector here and say 20 newtons, and this is the push that we received from the question that it said. So we've got a 5 kilogram box being pushed to the right. Now, one of the things that we want you to see, I hope this marker will show up good on the video, is that the vertical forces, the downward force and the upward force, our vertical forces, are balanced, they're equal. So that box is not moving up and down, it's perfectly still in the vertical direction. If there is no friction, then we can assume that back here, there is no force. So the only force acting on the box is the push to the right, and we're assuming that the surface is frictionless. So this 20 newtons we have unbalanced forces here. We have nothing to the left, but we have 20 to the right. So there's going to be a movement to the right, and we say that the net force is equal to the mass times the acceleration. So the net force, or the final outcome of all the forces acting on the box, is going to be 20 newtons, and the mass is still 5 kilograms. So the only thing we don't know is the acceleration, so we're going to divide both sides by 5, and the acceleration equals 4 meters per second squared. Does that make sense? Now, let's add something to this picture and let's see how it changes. okay? It's basically the same problem. I'm going to erase it and then redraw it right quick. Here's the tabletop, but this time I draw it like this in class, and I give the coefficient of friction to be 0.50. Okay, this symbol right here is a mu symbol, mu, it's a Greek symbol, mu. It represents the coefficient of friction, and whenever we have friction, I've always drawn those little diagonal lines like that. We still have the same box here that has the 5 kilogram mass. We still have a 50 Newton weight, and we still have a 50 Newton normal force. And let's say that it's still being pushed with a force of 20 Newtons to the right. Now, we have to deal with this friction. So if you remember back in your notes, the force of friction is equal to the coefficient of friction times the normal force. That's why it's so important to be able to solve for the normal force, because it's used in this equation. So now we're going to plug in 0.5 for the coefficient of friction, and we've got 50 for the normal force. And so 0.5 times 50 is 25 newtons. Now, the friction is going to be over here on this side. The force of friction is going to be 25 newtons. Well, we're only pushing with a force of 20. Do we have a large enough force to overcome the friction? The answer to that is no. So, first of all, if that frictional force is greater than the force that we have applied, the object's simply not going to move. You don't want to make the assumption that this frictional force is going to cause the box to move back to the left, because friction doesn't do that. Friction only attempts to take away motion. It's not going to cause motion. Does that make sense? Okay, so that's part one of objects sitting on a table. In the part two, I'm going to talk about forces that happen at angles. Thank you for watching.